everybody, it's time for some science. So it's been a while since I've been in front of the camera making a video for you guys. I am here in my wonderful home with all of my beautiful plants today, back in front of the camera to talk to you about solubility. And if you've ever wondered how rock candy is made, if you've ever wondered how they get sea salt out of the sea, well, solubility is something that you have to understand to answer those questions, to figure out how they do those things and how you might do those things if you ever wanted to make rock candy, or if you ever wanted to get salt out of the sea. So without further ado, let's have a discussion about solubility. But before we get into that, a word about today's sponsor, Jane Marcet. Let me read you a few things about Jane Marcet, one of my personal favorite chemists, from FamousScientist.org. She was a science writer, but that alone does not make her famous. In fact, she was the first female science writer. She wrote Conversations on Chemistry in 1806, but that does not make her famous. The reason why she is famous is because she wrote her book for girls at a time when education for girls was viewed as unimportant and unnecessary. And on top of that, she wrote this book in a way that anyone with little formal education could understand, and it became the standard text in chemistry education. This was a huge deal at the time because science was a field inhabited only by wealthy people. It was seen as something that not everyone could do. You had to have money to do it because up until 20 years before the car was invented, public education just wasn't a thing. Only rich people could afford to even know stuff. So she was one of the first people who brought the privilege of education to the everyday man, and that is why I personally love her as a chemist. On top of that, one poor boy born in 1791, whose father worked as a blacksmith, read this book and decided to become a chemist. He started work as an apprentice bookbinder at the age of 13 and went on to become one of the world's greatest scientists. That boy's name was Michael Faraday. If you want to know more about him, just message me and ask. I love the man. All right, now back to solubility. All right, so in Google Classroom, along with this video, should have been posted a set of guided notes. In fact, you may have seen the link to this video at the top of those notes. Well, I have them on the screen right here with me, along with a presentation about solubility. And what we're going to do is we're just going to go through this together and have sort of a conversation about what solubility is and how we can use it. So without further ado, let's get started. Solubility, as you can see by this detailed diagram, is heavily tied to concentration. In fact, it can be described as the amount of solute that can be dissolved in water at a given temperature. Maybe better described as the maximum amount of solute that can be dissolved in water at a given temperature. So let's write that down. Okay, and next, I'd like to pose to you a question, okay? For most solutes, do you think that they would dissolve at a higher or a lower temperature? Many of you are probably thinking back to the rate of dissolution stuff and saying to yourselves, well, I know that as I raise the temperature, things dissolve faster, so maybe I can get more stuff to dissolve if I raise the temperature as well. And you know what? You'd be right. Many things go up in solubility as the temperature raises as well. It's a direct relationship. To show you what I mean, let's graph out some solubility. So this is the solubility of barium sulfide. Basically, it's the number of grams you can get to dissolve in 100 grams of water at any given temperature. And what we're going to do now, and what I'd like you to do as well, is take a minute, pause the video, and try to graph this out on your own. I'm going to do it as well, and then we can compare. Okay, so as you can see by my admittedly kind of janky graph, as we go up in temperature, we can dissolve more solute per 100 grams of water. And so that means that we've got a direct relationship. As our temperature goes up, so does our solute. So as you can see by my admittedly kind of janky graph, we do have a direct relationship. As the temperature goes up, so does the grams of solute that we can dissolve in 100 grams of water. So we do have solubility going up as temperature goes up. Now let's look at a few more key terms. So some super important words to know in discussions about solubility are these three terms: unsaturated, saturated, and supersaturated. You probably saw these in the web quest. We're going to go into a little bit more detail about them here. So an unsaturated solution is one that's capable of dissolving more solute at a given temperature. So basically, we haven't dissolved everything that we could. For a saturated solution, it's not capable of dissolving any more solution at that temperature, and may have some leftover solute that's not dissolved in solution. So if I was going to draw that, I would probably have like a beaker with a little bit of solute left at the bottom. We'll talk more about how to draw them in a second. For a supersaturated solution, now these are super cool. They have dissolved more than possible at a given temperature under normal circumstances. We have done something to sort of trick the solute into dissolving more of itself into the water than it would normally be able to handle. These are super, super cool. We'll talk more about them in just a minute. Okay, so on our graph, to help us understand where those different types of solutions lie, let's go ahead and color our graph. We can color the area above it and label it saturated with undissolved solute, and the area below it we'll label unsaturated. Okay, so I just used the little polyline tool to make a shape that I could put over my graphs in order to color it, and then I labeled them. So as we can see here, I've labeled this unsaturated because if this is our grams of solute, then let's say we're at 80 degrees, anything in here, until we get up to that line, we can still dissolve more in it. But after we hit that, no more is going to dissolve, and it's going to be undissolved solute. That's just going to float to the bottom of our container. Let's see what that actually looks like right here. So as you can see, unsaturated solutions are going to be totally clear. Everything's dissolved inside of it, so it's going to look pretty similar to just regular water. For saturated solutions, if we get it right on the line, it's going to look the exact same way because it's got the max amount that can be dissolved in it, but it's all still dissolved. But as soon as we go above that line, we're going to start seeing undissolved solute that just settles to the bottom of the solution. So it's just going to be sitting there at the bottom. Let's go ahead and draw these. If you're doing it on paper, just do it with a pencil. I'm gonna attempt to use the draw tool to make this work. Okay, so here's my two pictures. You can see that in my unsaturated one, I just have some clear liquid in a beaker. For my saturated one, I drew some undissolved solute at the bottom, and I labeled it so I remember what that is. Always remember, where you can label your pictures, do so. It helps out a lot when you go back through your notes later and you're like, what am I even drawing? I have no idea what this is. Okay, so let's move on. Okay, so let's use our graph to figure out what amount of barium sulfide is able to be dissolved at 30 degrees C. And to do that, all we have to do, I'm going to do it on my notes right here, is I'm going to go over to 30 degrees C, and I'm going to come up and look at about where that is on the line. And you got to do a little bit of estimating. Like, it's probably not right on one of the tick marks. Looks to me to be about 9. And the way that I find that is I just go up to the line, right? There's 30 right there. I go up to the line, and then I go across, and I'm about at 9. That'd probably be a decent estimate to me. Okay, let's talk about this next question. If 45 grams of barium sulfide is added to the 100 grams of water at 60 degrees Celsius, then how much of the barium sulfide will end up undissolved in the solution? This one's a tricky one. Okay, so what do I know? I know that I have 45 grams of barium sulfate total. 45 grams. grams. And I know that at 60 degrees, we can only dissolve about 20 grams. I know that because I can look at my graph. It's right here. 60 degrees, I just come up, and hey, look at that. It lands at about 20. In fact, if we remember from the table, it's about 20.05. So what we can do is subtract that from the 45, because we know that 20 grams is going to get dissolved, meaning that everything else is going to get left over. So 45 minus 20, that would be 25 grams. Should be about 25 grams that we have left over. So now let's look at the solubility of a few different substances, and we can graph all of those out and make a more complicated solubility curve that can tell us a lot more. Alright, so at this point you should have a graph that looks a little bit like this, or maybe a little bit like this. It really just depends on how good your drawing skills are. Clearly mine are not amazing. Again, I got some pretty janky lines. Or, you know, it depends on if you're doing it on a computer or on pen and paper. But yeah, so we can use this to answer some questions down here. And again, I've got them all color-coded so that I can keep track of which ones they are. Let me fill in this color legend right here so that I can remember which color belongs to which compound. Alright, so for this first one, it asks us which solute is most soluble at 70 degrees. And if you look at the 70 degrees right here, you just run along the temperatures until you find 70 degrees Celsius. What you're looking for is the one that you can dissolve the most of at 70 degrees. You might be tempted to just look on up and see, oh, well, the purple one, which is, according to my legend, ammonium chloride, that one looks like the one that's at the top. But if you look at the red one, which is potassium nitrate, it is so high up that it's off of the scale. So by the time it would have gotten to 70, it'd be way up here. So it's gonna be potassium nitrate, because you can dissolve so much of it at 70 degrees, couldn't even fit it on the graph. Oh, pro tip for you guys. You know how a lot of formulas have subscripts, and so they have these tiny little numbers? If you want to very quickly go between larger font and those smaller subscripts on your computer, you can hit Control and comma. Control, comma will have you go between them. So if I hit Control, comma, I type in tiny little letters, and then I hit Control, comma again, and I go back to big letters. Just a pro tip from Mr. Cruz. All right, back to the video. All right, and we're back, and I'm just working with my graph from the notes here. So KNO3 was the most soluble at 70 degrees C. Question 2 asks us which solute is the least soluble at 35 degrees C. So we'll just come to 35 degrees Celsius, which is right here. And then we'll look for the line that is the lowest, which at this temperature, it looks like that is KClO3. So we'll just type that in. And remember the little shortcut that I gave you if you're doing this on a laptop. All right, question 3 asks us which solute's solubility decreases over time. That'll be the one that has a negative slope, and it looks like that is ammonia. Ammonia actually gets less soluble as the temperature goes down. Fun fact, that's because it's usually a gas. Gases dissolve better in water when the water is cold. It's the opposite of how solids work. Question number 4 asks us to look at the graph to figure out how much ammonia it would take to make a fully dissolved, i.e. saturated, solution at 30 degrees Celsius. Let's look at our graph. We'll go to 30 degrees Celsius here at the bottom, and then come on up until we hit ammonia, which was the blue line. I know because I can look at my key over here. So let's come up. and it looks like it's hanging around about 45 degrees. So, or sorry, excuse me, not 45 degrees. It looks like it's hanging about at that. So question 4 asks us how much ammonia would make a fully dissolved, i.e. saturated solution at 30 degrees Celsius. So what I'm going to do is I'm going to go on this is my x-axis where my temperature is in degrees Celsius. I'm going to go to 30 degrees Celsius, and then I'll come up until I hit ammonia, which is the blue line according to my key. So I come on up, and it looks like it's hanging out at about around 45 grams. That's where the line intersects. So 45 grams would be my answer there. All right, and finally for question 5, it asks if 75 grams of KCl, that's potassium chloride, is added to 100 grams of water at 50 degrees Celsius, how much solute would be left undissolved? Okay, well, to answer this one, the first thing that I'm going to do is I'm going to figure out how much would actually dissolve at 50 degrees Celsius. So I'll find my KCl line, which is green. So that's what I'm going to be looking for. I'm going to go to 50 degrees Celsius and then follow that up until I hit the green line. There we go. And that lands just under 40. So we'll say maybe 38. Again, it's a graph. We can be a little general about it as long as we're fairly accurate. I'm going to go with about 38 grams would dissolve in water at 50 degrees Celsius. So let's see. We've got 75 grams that we put in. So we put in 75 grams. About 38 of it dissolves, which means whatever's left, that's how much is undissolved. So 75 minus 30 is all we have to do. I prefer to show my work when I can, so let's see here. 75 grams added minus 38 grams dissolved equals, let me think here, so let me do some quick math in my head. So 38, 48, 58, 68. So that's 30. And then another, let's see, 5, 6, 7. So another 7 to get up to 75. So that's 37 grams. Correct me if I'm wrong. Someone leave a comment with the picture of their calculator to make sure that I'm not off. So 37 grams. 37 grams left over. There we go, and there's our answer. All we have to do is take the amount that we added, subtract the amount that would have dissolved. We found that from the graph, and there you go, 37 grams left over. So what I want to leave you guys with is a brief discussion about supersaturated solutions. I said we were going to come back to those. So what a supersaturated solution is, as I said before, you do something to the solution to get more solute dissolved in it than you typically could at that temperature. And if you look back at your solubility curves, like if you're doing these on paper, look down right now at your notes and notice that at high temperatures, we can usually dissolve more solid. So if you want to get more solute dissolved in a solution, you just heat it up. But what if I told you it's not necessarily going to undissolve when you cool it back down? Sometimes the solute will stick around in the solution ready to crash out at any opportunity, and usually all it needs is a tiny little crystal that it can build itself around. And what I want to leave you with is a totally different chemistry teacher who did this experiment back in, I don't know, like 2011 or something. His name is Dr. Ted, and he makes a supersaturated solution of salt and shows it crashing out of solution when he adds one of these little seed crystals. That's it for me. You enjoy the video. Super cool stuff. Fantastic everyday miracle of science. Have a great day, you guys. I will see you around.
So realize this has been sitting there all year long like this. Okay.
What is it?
I'm
What
gonna
is it?
change. Huh? Well, It's water that has a huge amount of these crystals dissolved in it.
Oh.
It has so much of it that it's called supersaturated. It actually is holding more salt than water actually can.
How does that work?
Because I boiled it.
You dropped it in there?
What?
Oh snap!
Oh my gosh, that's so cool!
It looks like a
pretty
sea
It looks like a
urchin.
looks like a
Looks
puff
like a sea
ball.
urchin.
My finger ran out of
Oh my god.
Oh my god.
That's so cool.
It's so
What happened to the bug?
What happens if you? It's still over there.
That's
Ow!
so cool.
It's still
That was
right,
just one
it's
drop.
right there.
One crystal.
Imagine.
Look at it extending from the bottom.
Oh, that one's racing. It's racing. Look, that one's Jeremy. He got it.
Yeah, I get there first.
Watch it break.
I want to see my nail. I want my nail to be in the picture.
Oh my gosh, Elijah. This is giving me goosebumps.
It does look kind of weird.
This is so cool.